You get to meet people. There's the secret track, which is just walking around, having a coffee, talking to people you don't know. Oh, what do you do? I do this. You learn so much and you extend your network amazingly well. And you cannot do this online. It has to be in person.
Okay, guys, thank you for attending my talk on modern C++ for bundle adjustment. My name is Vishnu, and I am an engineer at Zebra Technologies. We focus on making robots for warehouses. We sell picking solutions so that people and robots can work together to complete a fulfillment order. Okay, the outline of the talk is shown here. I'll be talking about visual reconstruction, what it is, and the dataset that I'll be using, which is from the paper Bundle Adjustment at Large. I'll be talking a bit more about the structure from motion pipeline that I built, the data parser that I'm using here to pass through the datasets, Outlier rejection, optimization, and finally the results. Okay, so the problem statement that I'm trying to tackle over here is I want to build a robust, scalable, and adaptable pipeline, which can deal with multiple types of datasets and also is a bit more resilient to outliers and is scalable. So why do we need to do this? The reason is that there is no uniformity around the types of datasets in visual reconstruction. There are datasets such as Kitty, BAL, which have a different format, which have different parameters for cameras, which have medium to large sized points in it. So there's no uniformity over there. So when you build an SFM pipeline, you need to make sure that your pipeline can adapt to these different types of datasets. So that's where data diversity comes in, and that's something that you would want to tackle. And then because of these datasets being a real world datasets, there is an element of noise and outliers in the dataset. So you would want to have a special catch over there to make sure that you are accounting for outliers and filtering them out before you pipe them in. And then scalability. Scalability and optimization goes hand in hand. You usually want to work with a large-sized or mid to large-sized data set, and those are in terms of millions of points. So unless you're able to account for that millions of points, or maybe in 500,000 of points, your SFM pipeline is not going to work. So you need to make sure that your pipeline can process those number of points, give you a good result, and is also pretty flexible. So before we jump into the pipeline, just a quick talk through about visual reconstruction. Yep.
Sorry for interruption. So you're talking about very generic things. Can you explain a little bit in what domain are you talking? What pipelines and what points in your specific topic?
My topic would be modeling the SFM pipeline using outlier rejections and then using two variants of optimization.
So we're talking about ML, geometry?
Geometry mostly.
Okay.
Cool, yeah. Before I jump into the code, just a quick walkthrough about visual reconstruction. So the idea behind visual reconstruction is to infer 3D structure from a set of 2D images. And because this talk is mostly going to be about visual data, I'll be focusing mostly about camera inputs, but reconstruction can be done also with a LiDAR, radar, or any other sensors. All you need is a distance measurement and an angular reading. As long as you're able to point where the measurement is coming out from, you'll be able to do visual reconstruction. So like I said, the inputs are multiple images and the outputs would be a 3D reconstruction. The challenges over here is that you have to account for missing data, you have to account for occlusions, noise, outliers, and you have to make sure the pipeline is resilient to processing about 1 million number of points. So this is a quick example about how it'll look like. So on the left, you can see the three main components of the pipeline, which would be the cameras, the observations, and finally the 3D model. The 3D model will basically be the landmarks that you're trying to map out. And one thing to note over here is that there are multiple cameras looking at the same part of the 3D model. This is because you would want a significant overlap and also associate measurements with those observations. And The observations would be the information that's present on the image plane, which would be the UV pixel coordinates. And finally, you have the moving camera, which could be either one camera or multiple cameras. And you would basically be getting camera poses to optimize on to get a good reconstruction. And on the right, you have an output from GlowMap, which is a reconstruction of a building using multiple cameras. So a key idea over here is that you would need to have multiple cameras looking at an object from a different variety of angles to get a good angular field of view. Without a good angular field of view, you won't be able to triangulate and estimate the poses properly. So a quick walkthrough over here, you have input data, which is from cameras. You extract features from it using corners, corner detection, or YOLO models or hog-based histogram over gradient methods. You associate each landmarks to, you associate each observations to a landmark so that you know, so that you're able to have multiple observations from multiple landmarks and make a system through that. Then you estimate seed poses for the landmarks and cameras so that you have a seed pose to provide to the optimizer, which the optimizer can wiggle around and get a good estimate. Then you do pruning to make sure that you are removing noisy data or accounting for them. Do bundle adjustment to minimize the reprojection error. And finally, you reconstruct the setup. So the dataset that I'll be working on is from the paper or the project Bundle Adjustment Large. I will be mainly showing results from the datasets Ladybug and Trafalgar Square. So this is an interesting dataset because it already does association and also provides me seed poses for the landmarks and the cameras. It is also designed for a mid to large size problem, which are more of the interesting types. The format's also pretty interesting because it gives you the number of cameras, points, and observations, and it first gives you the observations, which is between a camera and a point and the position of the point in the image plane. And then it gives you the poses of the cameras and the poses of the landmarks that it's trying to map. Okay, so this is the Ladybug dataset. This is a pretty interesting dataset because you have more than 500,000 observations. You have 1,700 plus cameras and that many number of points. The reprojection error over here is also interesting because you have a mean of 3.8 and a max of 1,600, which shows that this has a long tail for this dataset, and the long tail is mostly going to be the outliers. The observations per camera is also pretty interesting because you have an observation of, there are some cameras with 0 observations and a max of 970 with a mean of 393, sorry. And then observations per point also is pretty interesting because you have some points with just 2 observations and some points with 145 observations. So this is a pretty diverse data set where you have points with good number of observations, good field of view, and also bad observations with a narrow field of view. And then you have the Trafalgar Square dataset, which is a mid-sized dataset with about that number of observations and 257 cameras. This also has a high max of 456 reprojection error, and also observations camera is a bit more denser than the previous dataset. We have 876 as a mean with a max of 4,000 observations from a single camera. And the observations per point ranges from 2 to 42. So again, the challenge over here is that these are huge data sets with around 500,000 points. And if you don't account for the noise and outliers in these data sets, then you end up having a non-convex optimization. So last slide before we jump into code. Just want to talk a bit about the projection pipeline because this ends up becoming the backbone of the whole optimizer and the outlier rejection. So I'm using a radial distorted camera model here. It's a pinhole camera model with radial distortion along with it. So what is that? So that basically means that you're having parameters about the curvature of the camera's lens, and you can account for that when you're optimizing. So how does this projection pipeline work? It works pretty simply. It's a pretty straightforward pipeline. You get a point in the world frame. First, you move that point to the camera frame using the camera's pose and translation. Then you move it to the normalized image plane, which is a simple concept for saying the depth is 1. So you end up dividing the x and y by the depth. And then you account for the radial distortion and you correct for it. And then you use a focal length to get the pixel coordinates. So this pipeline becomes a backbone because once you have a 3D estimate of a point in the world space, you can use this pipeline to figure out where it lies in the image plane. And then you can compare that prediction with the actual measurement of the point in the image plane. And that ends up becoming the reprojection error that you're trying to optimize over. Okay, so this is the pipeline that I'll be talking about for the rest of the talk. So my goal when I was making this pipeline was that I wanted to make it as modular as possible and also scalable. And I accomplished that using C++ concepts. Using concepts, I'm able to set up a foundation for policies over here. What I mean over here is that by using C++ concept, I am setting a set of rules that each modules need to follow. And this becomes a contract between the pipeline and the modules that it's communicating with. So as long as these modules are able to follow the set of rules, then it can easily communicate with the pipeline, and maybe even the user can even switch in and out different modules based on the set of rules. So this lets me deal with a variety of datasets as I'm expecting the data parser to pass through the dataset and give me a data object that follows a dataset-like policy. Then I'm able to switch between multiple types of filtering using the outlier rejection policies, the spatial filter policies, or the optimization policies. And I'm also accounting for scalability by having a policy over the windows. So this is the pipeline, and we'll be going through it one at a time. So first, we'll be looking at data parser. Sorry. So data parser is pretty straightforward. The main goal over here is that I needed something to pass through the data set and give me an expected output, give me an output that I can work with. And because this is an expensive function, I'm using a no discard keyword over here and std expected to account for any parser errors. The no discard gives a compiler warning or an error if a user accidentally calls it without using the return type. And std expected helps me with the exception handling. The main 3 goals over here with this function or with this class called data parser is that I need to do some basic filtering, preprocessing. Then I need to normalize the data so that the ranges of the cameras and the points that it's dealing with are in almost the same range, and also convert it into the policy format that I'm expecting. Okay, so filtering. So the pre-filtering step is very straightforward. I'm just making sure that the data I'm processing is bit sanitized. I'm making sure that the camera IDs are valid, and I'm also making sure that the landmark when transformed to the camera coordinate frame is at a reasonable distance away from it. This is basically like it should be around 0.1 meters or like 10 centimeters away from the camera, just so that it's a valid landmark. And the thing over here is that because it's a large data set, you would want to parallelize this. So I am using std for each with an execution policy or a parallel execution policies. I'm using the Intel TBB library over here to use this parallelization. This helps a lot in speeding up the processing of the dataset, and I kind of became a huge fan of this property. I'm also using erase to erase any landmarks with insufficient observations. Basically, any landmark with less than 2 or less than 3 observations, I'm removing it. and then processing everything else. Normalization. So the idea behind normalization is that you don't want the range of values for the data set and for the cameras to be very different, or have a significant difference between the ranges over there. And this is because the optimizer won't be happy if the ranges are too wide apart. The optimizer will end up moving the camera and optimizer will end up moving the cameras or the points by a varying different amount, and that can cause a non-convex optimization. So the idea over here is to use MAD to normalize the data so that all the inliers are around the same set of ranges and the outliers are projected out. This does not ignore any outliers, but rather make sure that the inliers are clumped together while the outliers are pushed out. And I'm using MAD over here over mean because the median is a bit more resilient to outliers than mean. And so that means that I'm just using the inlier cluster for normalization over the mean. And again, I'm parallelizing using STD for each using Intel TBB. Yep.
So how big is the landmark when you do the parallel? How big? How many of them?
So landmark, I can go back. So landmarks are 65,000. I have 65,000 points over here. Those are the landmarks for the Trafalgar Square dataset, and for Ladybug is 156,000.
So you don't need like a GPU for that?
No, I was running on my laptop over here, which has an Intel GPU, but not a custom GPU. Okay, so moving on to the policy. So this is a part of the input policy that I am modeling, or I'm setting as a set of, that I'm using as the API contract between my pipeline and the data parser. So we have three components here. One is the camera model-like, then the camera-like and observation-like. The camera model-like uses the main function that the camera model-like, there are a set of functions over here, but when I started writing this out, I just wanted the model to have a project function. The project function basically projects a point from the camera frame all the way to the image frame. And that, at the end of the day, that's all that you want. You don't want anything fancier than that. You just want the camera's intrinsic model to just project the point from the camera frame all the way to the image frame. But I ended up adding focal length, principal point, and distortion coefficients because since the optimizer can now wiggle them around, you would also expect that the input policy asks the data parser to provide that to you so that the optimizer can optimize on the intrinsics too. So that's why those three are added over there. The camera-like is the camera extrinsics. It has the intrinsics along with the translation, rotation, and the ID. And the observation-like is the policy around the observations. So an observations between a camera, landmark, and camera, landmark, and it also provides you the point in or the location in the image frame where the observation was observed, which is the pixel coordinates. Then for the whole data set, so the output for the data parsers would be an object that follows this policy called the dataset-like, which the dataset-like policy kind of encompasses the previous two policies in it. So the dataset-like expects the dataset to have these three main functions, which is the observations, cameras, and points. And the return type of those three functions should be of type observation-like and camera-like. So I'm setting these policies or like these set of rules over here so that I can have an API contract with a data parser or anything that parses through a data or a text format. And also I'm adding an STD map over here, or like two return types with STD unordered map. This is because this kind of helps out when you're doing a query. You can query an observation from a camera's point of view, an observation from a landmark's point of view, and just having this kind of speeds up the whole thing from on the optimization end. Now moving on to the pipeline. Sorry. For the pipeline, I set it up using a factory design pattern. The idea over here is that using ROS configs, I can switch between different types of the pipeline that I want. I can use a balanced pipeline that works with lesser quality or a lesser powerful outlier rejection and optimization, or a high performance one that works with a more compute extensive pipeline. And because it's a factory, I'm also expecting the user to write the derived classes which inherit from a defined base class, which defines the policies. So the reason I did it this way is for two benefits. One is that I can switch between variants at runtime, and I also have a compile time check to make sure that the user's implementation of the policies are valid and it follows the policy requirements. So this is the main hybrid pipeline class. So as you can see, I have templating on 6 types, where 5 of them have a requirement that they need to follow. And one more thing to note over here is that I'm passing the data set type into the other policies too, to make sure that the other policies are okay with this type of data set that we are using over here. And just a quick overview over here. This is the factory that is producing based on the user-defined type, which is got through the params. So you have the balanced hybrid pipeline, which inherits from a base class which has defined these implementation policies, and high performance one, which inherits from this base class which has these defined inherit policies. So by defining them in code, you have a compile time check. Make sure that you are not going to run invalid version of the pipeline. The main function is pretty straightforward. It just does, it generates the windows, then it performs outlier rejection, and then finally performs optimization. I kept it as simple as possible because I'm expecting the modules to do the heavy lifting. So yeah, logging and window policy. So the logging policy is pretty simple. It just has to log the message, and that's it. So an implementation over here is a ROS logging policy, which uses CPP, debug, info, warn, and error. It's pretty straightforward. The interesting thing over here is a static assert. Static assert. So thing about logs is that it's pretty easy for a library to have multiple different versions of logging, and you'll only end up using one, but you will still end up implementing multiple ones. To make sure that all the different versions are compatible with the policy, you can use a static assert and check and do and use the compiler to check if the policy is still valid or the implementation is still valid. Yep.
Don't you lose the source location information by doing this? Those macros give you source location information in your log output. And by putting them inside this function, you're going to lose where you call this.
Yeah, I think so, yeah. So I'm expecting the message to have that information. Maybe I can constrain the message or have another field over here that has the source location information. But right now, I was expecting the message to carry that information with it. Nice catch, though. The windowing policy is pretty straightforward. I'm using a non-overlapping window. It can get pretty complicated by using an adaptive window or overlapping window. But for the purpose of the talk, I just kept it simple as a non-overlapping window. And this is the windowing policy. It's pretty straightforward again, expecting generate windows function and a window result as the output. Not going too much into detail over here for the sake of time. Okay, outlier filtering. Outlier filtering, I kept the policy for outlier filtering again pretty straightforward. I have a reject outliers function that is trying to call, and an outlier rejection result that I'm expecting from it. The rejection result is basically just, for now, is basically just some stats that I want to infer from the from the operation, the inliers that it found, the outliers that it ignored, and the inlier ratio. I'm doing a simple outlier filtering over. Yeah. Sorry.
Oh, on the previous slide.
Yeah.
What is the destructible for?
It means that I'm expecting the class to do a destruction clean of the memory and make sure that a destructor is defined. Okay, so the simple outlier filtering is actually pretty straightforward. I end up using the projection model to project the landmark onto the image plane and check if the measurement versus the observation, or measurement versus the prediction is within a bounded, within a threshold. If the projection on the image plane has a high error, then I'm ignoring it. If it doesn't, I'm keeping that particular observation. Now, this is pretty straightforward. The challenge over here comes up when you are dealing with more than 500,000 points. You have to iterate over each point, implement a projection or like do a projection for each of those points and project it back to the image plane and check. So that becomes a bit heavy. So what we can do over here is basically decouple the problem. You have multiple cameras over here, and each camera is independent of each other. And each observation within a camera is also independent of each other. That means that it's giving you the ability to parallelize. And you can parallelize basically at the camera level and also at the observation level, so that you have a significant speed up. And so that's basically what's happening over here. I'm processing at a camera level by using STD execution power. And also I'm processing at observation level by using STD execution power. So I'm getting the reprojection error per point using the STD transform over here. And then for iterating through each point and its reprojection error, and then filtering them out. This ends up becoming really fast. I don't have to do sequential. Each will be done independently. And each point has its outlier function. Sorry. Each observation has a field called its outlier, and that gets toggled if the error is too high. Now moving on to the spatial filtering. Spatial filtering is also an interesting concept over here. So you might be wondering why I have two stages of filtering, filtering from a simple outlier and also spatial. This is because you would want to tackle the outliers from two different points of view, one through the image, one in the image frame and one in the world frame. So in the image frame, you can do outlier filtering, RANSAC, while you can do spatial filtering in the world frame. So that the idea behind spatial filtering is that you would want the 3D projection of the model to be as smooth as possible. So if there are some points that are lying outside this smooth model, then those are most likely to be outliers. The policy is pretty straightforward. Filter spatially is a function that I expect the model to call, model to implement it, taking dataset and camera window. And the result is going to be a spatial filter result that I'm expecting from it. So like I said before, this filtering is happening in the 3D space. So you have a bunch of landmarks that will be grouped together, and there would be some outliers that would be present beyond the range of those landmarks, or beyond those clusters. The idea is to catch those outliers that are visible or present far away from the clusters and filter them out. So this means that I need to iterate through each landmark or each point over here, and then find its nearest neighbors, calculate the mean, and then see how much standard deviation is a landmark away from that, is a point away from the bunch of landmarks near it. This is an expensive process because, as we've seen earlier, you have a lot of landmarks, a lot of points, and now I'm asking you to find its 100 nearest neighbors or 200 nearest neighbors and calculate the mean and standard deviation. So this is expensive. So the way to deal with this is to use a boost R tree. Boost R tree already groups elements in it using a spatial index. So using the property of a boost R tree, you are getting a spatial grouping for free. You have one cost where you need to load all the points into the R tree. And after that, everything's based on a query. You can keep querying the R tree for each point, figure out its nearest neighbors, and then perform a filtering on top of it. Yes. So this came in clutch for me, sped up the whole process. So the idea over here is the same as earlier. We only so idea over here is that because there are two stages of filtering, you can ignore points that are already defined as outliers by the previous filter and only process points that are defined as inliers or like pass through the previous filter. So you speed up over here by ignoring points that are already passed as outliers. And then similar to the previous approach, each camera and each observations are independent. So you can use the parallelization over here to speed up the processing too. This is a bit wordy, but what I'm doing over here is I'm finding the mean and variance, and I'm using z-score over here to check whether a point is an outlier or not. To calculate mean and so first I'm finding first I'm finding the k nearest neighbors of a set of point, and then I'm using std ranges for left to calculate a sum and a squared sum to calculate mean and variance. And then I'm using doing outlier filtering using that. Thing to note over here, at least from an algorithm point of view, is that I noticed a mistake after I made all these slides. One is that I'm approaching this problem from a camera and observation point of view, but rather I could have just parallelized from a point of view. I just needed to iterate through all points and then query the neighbors of the points and filter using that. Instead over here, what I'm doing is that I am going through each camera and each observation in a camera and then checking which all points are observed by those observations. So there's an inefficiency over here, but yeah, just kept it in to show that, yeah, it happens. And you can also make this a bit more smarter. One assumption you can make here is that the mean would be locally consistent up to a particular radius. So you can assume that some points that are nearby each other would have the same mean, and you can cache it. And then you can do just a query for the mean from a hash map. So that would also speed it up. But yeah, that is part of the future works for this filter. Now, after doing that, you end up having something like this. Yeah, for the Ladybug data set, you end up filtering out 3.3% of the points, which has a mean error of 21, standard deviation of 36, and median of 19. I'm guessing there's some inliers that are also getting caught up over here. But standard deviation of 36 means that you are ending up catching the outliers that are in the tail end of the Gaussians. Then for the Trafalgar Square dataset, I'm getting a mean of 37, standard deviation of 19, and mean of 34. This looks a bit more better. The median and mean are somewhat consistent. I'm also ignoring around 8% of the points. Okay, moving on to the optimization. The optimization policy is pretty consistent and easy to understand too. I'm expecting an optimize function to be called by the policy implementation, and I'm expecting a summary of result. This summary helps in kind of figuring out the quality of optimization. You can go through the cost change, whether it was successful or not, and the iteration summary that gets outputted by Ceres. The idea behind optimization. So the concept of optimization is pretty straightforward. At the end of the day, you want to reduce your reprojection error. And what you have with you is that you have the measurements, you have the camera poses, and you have the landmark poses. So now what you're asking the optimizer is that you are asking the optimizer, hey, reduce the reprojection error, and I'm allowing you to wiggle around the camera poses and the landmark poses. Wiggle them around as much as you want, as long as the net repro error of the whole model reduces. And a thing to point out over here is that the observations are kept as constants while you're only moving around the 3D point and the camera poses and the intrinsics here. So you end up reducing this expression over here.
Is your cost function pretty much fixed for this problem?
Oh,
Or you
yes.
have different kind of-
No, it's fixed for this problem. I am varying the loss functions, but the cost function is the basic reprojection model.
Okay, but the loss function could be different.
Yep. Loss function can be a Cauchy-based loss function or a Huber loss function. I'm also trying out, I also tried a variant where I am creating my own adaptable cost function, but that didn't end up giving good results. So I'm sticking with Huber or Cauchy.
So when you change a different loss function, do you use any of the like automatic differentiation library, internal, external, or you hand coded the backward?
No, I'm using the Ceres autodiff library. The Ceres Solver has an autodiff solver, which produces the Jacobians for me.
That's from outside of your company, or
That's from outside the company. It's a publicly available solver called Ceres Solver. And this pipeline is built using that. So the idea behind linearization is pretty straightforward. Because you're inherently solving a nonlinear problem, you have to linearize it. And to do that, the Ceres solver uses something called Taylor expansion. It breaks down the problem. It breaks down the problem into that expression see over there. So fx plus delta, with delta being the small change in estimate that you want to do to reduce the error, gets broken down into fx plus j delta, j being the Jacobian. And then you expand that expression to get this normal equation, which is Hessian into delta equal to minus Jacobian into residual. Because we are solving a bundle adjustment problem, you have one thing in your advantage, which is that the Jacobian matrix that you're solving is going to be sparse. This is because each residual, which is the reprojection error, only depends upon one camera pose and one landmark. So you end up building a huge Jacobian matrix, which is basically going to be sparse. So you can use something called Schur complement over here to express the points as camera poses and solve a much reduced system. And then once you solve for the camera poses, you can back substitute into the to get your point estimate from those camera poses. So basically what will happen is that if you have a million or more points in your data set, instead of having a million cross million Jacobian matrix, you end up compressing it to only camera poses and you solve for the camera poses. And this ends up giving you a huge advantage in speed and also in memory. And the Ceres solver has two strategies that it recommends, the Leeuwenburg market and the dogleg. I mainly use Leeuwenburg market because I think it's a bit more faster. And it also uses something called a trust region-based strategy, which makes sure that the step size doesn't overshoot for a poorly conditioned problem. The step size over here is an interesting concept. If the function is not well conditioned, as in if the function has a lot of valleys and deep pits, then a wrong step can end you up in a local minima, or you might end up taking a large step and not having a significant reduction in your error. So using this trust region strategy, you can account for that. If you are taking a step down, or if your delta is not reducing the error by a significant amount, you end up not trusting that delta, and you end up reducing how much you're moving along in the direction. But if your delta is significantly reducing the error, that means that you are going the right path. So that means that you can take a larger step and continue iterating through. And finally, you update the parameters and then you reiterate. So for the simple bundle adjustment, what I implemented was that I'm using the cameras in the non-overlapping windows, and I'm using the observation by those cameras, and I am optimizing on top of that. So any camera's observations outside the window are being completely ignored. So yeah, like this, it'll be processing one step at a time. And this is how you end up breaking down the huge bundle adjustment problem. You end up breaking it down into sizable chunks. And using this windowing-based policy, you can process just a small chunk at a time. And finally, you are assuming that by processing smaller chunks, you end up lowering the cost of the whole problem. This is the optimizer settings that you set for the Ceres solver. And so how Ceres Solver works is that it expects you to store all the variables that you are, it expects you to store all the variables that you want to optimize into a vector, which is the camera params over here. And then it takes the pointer to the data inside the vector and it optimizes that. So over here, I am first I'm using a lazy approach to using STD views to iterate over camera with observation, which is basically the qualified set of cameras within the window. And I'm getting the camera parameters over here, and I'm storing the camera parameters inside a vector. And I'm passing that vector, or passing the pointer to that particular vector into the Ceres solver using add parameter block. And I'm also using quaternions over here, not a rotation matrix. The idea over here is that quaternions are much more stable than rotation matrix, and I can also use the quaternion manifold to restrict the optimization space for the quaternions. This is because if you don't use the quaternion manifold, Ceres would be allowed to move the quaternions however it wants, and it ends up becoming an invalid rotation. By using the quaternion manifold, you're restricting the Ceres to restricting the solver to basically move the points in the SO3 manifold space and keep the rotations a bit more consistent. Yep.
Sorry, how did you tell Ceres to constrain it to the normalized quaternion?
I don't think I added it here. Sorry about that. But you can add a product manifold or a Ceres quaternion manifold. So you would basically be adding it over here along with the parameter block, telling that this part of the parameter is a quaternion and respect that and don't optimize it to an invalid point. So same idea over here for observations. You iterate through valid observations using STD views and then store the observations inside the point param storage and pass in the pointer for that particular storage into Ceres into the solver so that the solver can modify it when it's optimizing. So the idea behind the solver is that the solver takes in these pointers, modifies it, and then you are expected to process a vector again to read what the new processed term is, and then update your dataset with the new processed term. So that's what's happening over here. You iterate over the vector again to figure out which camera ID corresponds to which part of the vector, and then you update the values of the cameras with the new results that the solver has provided you. But your reprojection error explodes when you do this. Even though you have accounted for outliers and you have broken down the problem into smaller sizable chunks, you end up having a high reprojection error than what you started off with. So something went terribly wrong in our process. So the mistake that we made over here is that we are assuming that the problem is, or the chunks of the problem that we're solving are completely independent. And that's not true. From the camera point of view, it might be independent, but from the point of view, it's not. This is because there are observations that are shared between multiple cameras, and you can take advantage of that in this problem over here. So that's what I basically did. So instead of only adding cameras that are in the window, one method to improve this problem is that You can add all the cameras in the dataset, but only set the cameras that are in the window to be variables, so that the optimizer will only be moving the poses of the cameras in the windows and ignoring everything else. And then as you change a window, you end up resetting that. You end up resetting the cameras that are not in the windows to be constant and the cameras in the windows to be variables. So in that way, you end up covering the whole problem and only optimizing a particular chunk of it. And the other thing I did was that I can introduce a lower bound and upper bound to the optimization space. This basically restricts the space that Ceres can cover or the solver can use to move the points around. So right now I am using constants over here, which is focal min, k-min, k-max. And I'm using these constants to set up upper bound and lower bound for the set of values that the solver can use to wiggle around. But to make this a bit more smarter, what you can do is that you can pre-process the dataset to see the range of values that is covered by the dataset and restrict the space by using that information. So that way, your solver would be able to solve different types of dataset without actually changing these into hard-coded values. And then the second thing I did over here was that instead of only accounting for observations in the current window, I'm also accounting for observations outside the window. So the idea here is pretty straightforward. So the first thing is that I am introducing a new param called in-window support, which basically means that if a point only has one observation in a window, don't optimize that point or don't use that observation. This is because if you just have one observation, you end up over-optimizing for that observation and end up with a local minima for the point. And when you process that point again in the next window, the point ends up being the wrong spot for optimization and the thing collapses. So using in-window support, I'm able to tackle that case. And the other case is that a point might have multiple observations from multiple cameras outside the window too. So we can take advantage of that. So I'm adding residuals for all the observations of a point outside the window too, but I'm setting the cameras as constants. So that means that the solver ends up solving only for the point pose and not the camera pose for any cameras outside the window. And these observations can be has an anchoring effect over here. It makes sure that if you're moving the point and the camera for the cameras in the window, the solver would use the other observations as a way of anchoring them down, anchoring the point down. And I'm also using lower bound, upper bound over here, and I'm setting the points in the dataset as constants or variables based on the number of observations that they have. Two other things that I'm doing over here is that I'm introducing something called parameter ordering. As I said earlier, you can use Schur complement to break down the Jacobian or shrink the Jacobian into only camera poses. But one thing the solver expects from you is that you order the problem in a right way. What I mean over here is that the problem expects the cameras to be in the top part of Jacobian and the points to be in the lower part of Jacobian, so that when it replaces the points, it just ends up taking the point chunk of the matrix out and replacing that with camera poses. So to do that, it expects you to order your problem in a particular way, and you can do that using parameter ordering, which is a concept in Ceres on the solver to make sure that the cameras are in the top part of Jacobian and the points are in the lower half of Jacobian, and you add them to the 0 element group and the first element group. So this helps in making sure that, so the solver is expected to do this for you in the backend, but by explicitly calling them out, you are telling the solver or you're helping the solver by speeding it up and making sure that it gets what you're solving. Then another interesting feature of the solver is the inner iterations. The idea over here is pretty straightforward. Instead of using a joint optimization to solve for both points and camera poses, you can decouple the problem. You can do the main optimization first, and then you can do a series of inner iterations or inner optimizations where you fix the camera poses and optimize only the points. And then you can fix all the points and optimize only the camera poses. This is advantageous for us because each subproblem is much simpler and easier to solve. But the problem over here is that you're using the Jacobian that you use for the joint optimization. So if your function is heavily non-convex, then you end up using a bad Jacobian multiple times, and you could have a bad optimization. And you also add more iterations over here that can end up using more compute. So this is kind of a double-edged sword. You need to kind of try it out, make sure your function is properly preconditioned before you can use it. So this is something that's worth trying out, but always be a bit concerned about it. Then I did try introducing two loss functions, Cauchy and Huber. Huber is quadratic loss until a threshold and then linear loss beyond it, while Cauchy is quadratic loss to a threshold and then log beyond it. The advantage over here is that you can use Cauchy loss if you have a lot of outliers in your dataset. Because introducing a log loss beyond a threshold, it ends up heavily deviating the outliers. And Huber is a linear loss, so it doesn't heavily deviate them, but it reduces the impact of outliers into the residual. This is something you have to play around with. Using a loss function using a loss function also means that you tune it because you are reducing the impact of residuals. Your optimization problem might not converge in time, or optimization problem might take more time to converge because you are now moving from a quadratic to a linear loss. So you need to play with the thresholds and figure out what the right threshold is for you so that you converge with just inliers and you ignore the outliers. And yeah, I did try using a custom loss function. I don't recommend it. I recommend using whatever is set up by the solver. This is because it ends up becoming more of a hassle than advantage. You need to mention the residual that you're solving, and also you also need to provide the first order differentiation, second order differentiation, third order differentiation of the particular residual, which ends up becoming complicated. So doing this, the average reprojection error ends up becoming much more tolerable. You end up accounting for outliers and also having decent 3D modeling of the world. There are still some noise on the sides which needs a bit more of tuning and processing, which needs to be done as part of future works. Some references that are used for this talk. To know more about the solver, I posted a link over here, and there's also a talk by the author of the solver, Samir Agarwal, which I highly recommend. It gives a good overview of how the solver works. Yes, any questions?
Hey, thanks for the excellent talk. 2 questions. First one, I might have just missed it. Did you use any sort of features to be able to associate landmarks together that you used for this?
No, the dataset already did data association for me.
Okay.
So I was using advantage of that. But the filtering is to make sure that we account for any error in association and make sure you push that out.
Okay. And then the other question was that earlier on you used a factory to create the different things, but you still kept all of those objects together and used a bunch of pointers. Is the reason that you didn't just make it a function and then have them as concrete objects?
No, I don't have a good answer for that.
Okay.
I just end up implementing that way.
All right. Thank you.
Hi, great talk.
Thank you.
So in a similar problem that my company has, a problem is one sensor with many more observations than others, where they're all sort of biased. So maybe all of your measurements are shifted to the right. When you do the cost minimization, you tend to prefer to bias the net result towards that one camera. So maybe I didn't catch it, but where within the pipeline do you take that problem into account?
So you would want to introduce a new optimization module which has a weight parameter. So you would want to or that will basically be the information matrix or covariance matrix you're passing in. You would want to lower the weight on the residuals by the camera with more observations so that you can equalize the weighing or equalize the effect of the residuals between multiple cameras.
Okay. Yeah, thank you. That's similar to what we've used before.
Okay.
So it's good to know. Thanks.
Thank you. I had two questions for you. Do your 3D reconstructions have known scale since you have both the intrinsics and extrinsics calculated?
Yes, they do have a known scale.
And are they of reasonable scale? Have you?
So I am rescaling them again using the normalization to make sure that it's within a reasonable range. But if you just print out the data set, it ends up becoming pretty okay to observe. It's not as if the cameras are very far away from the point, but to account for that particular issue, I am renormalizing it using median absolute deviation.
Thank you. And then have you tested with constraining the intrinsics of the cameras to be the same if all the images were from the same camera?
Good find. It's a good catch. I want to try that out, but I didn't do that.
All right. Thank you.
Yeah.
Could you back up a few slides, please? There's a color for each. When you start talking about a new method. Yeah, here. We don't use parallel policies because the lambda is overlapping. It's not thread safe anymore.
So this one I'm not using parallelization. This is sequential because I'm not specifying the parallelization policy here.
Right. But can you? I mean.
Oh, can I?
Or
I think so.
are they independent calculations?
The observations are completely independent, so you could do it in observation space. But if it's because it's points, you might want to make it thread safe with mutexes around visited points because multiple observations around.
Okay.
Yeah.
So do you think this will be slower? I don't know how big the data is.
No, I don't think this is much slower because the reason is that you are only looking at points that are observed by the previous window and the current window.
Oh, so
And
your window size is small.
yeah, it's already small. Yeah. Cool. Okay, awesome. Thank you, guys.